Okay, let's go for the next experiment. In this case, it's gonna be diffraction. When we have diffraction, we have light going through an opening, for example, or go to an obstacle, right? And the wavefront is distorted. In this case, we have an opening, right? With width or diameter, in case we have a circular opening, it's gonna be the width W, correct? So the pattern that we're supposed to find is coming in this way. So we have at the center most of the light, or a big spot, right? Bright spot, right? Or bright fringe is right here at the center. And then we have that the intensity decreases, right? Going away from the center. So in this case, we have, let's say, constructive interference or bright fringe. And then we have dark fringe, bright fringe, dark fringe, bright fringe, and so on. The same thing on the other side, correct? In this case, we're paying attention on the dark fringes. The first one is labeled M equals 1, the second one M equals 2, and so on. Okay, the equation for diffraction is coming in this way. W sine theta equals to M lambda, right? This is the angle from the center to the dark fringes, correct? Now, because the angle is small in this experiment, we make this approx, right? Sine theta about tangent theta, correct? When that happens, right, we make a right triangle, and tangent is y over L. L is the distance from the diffraction slit right to the screen. In this case, it's gonna be 3 meters, right? When we now apply this condition, right, and tangent using y over L, we get this equation for the experimental lambda. Today we're looking for lambda of the laser. The theoretical value is 532 nanometers. So let's look for the experimental value using W, Y, M, L. M, remember, is the order number that is used for diffraction interference, right, cases. Perfect. We have 3 parts. Right here we have part 1, the width 1 equals to 0.116 millimeters. The second one, 0.08 millimeters, and the third one, 0.04 millimeters. Correct? Now let's do only for M1 and M2, right? Per A is M equals 1. Let's find Y. Y1, right? The distance from the center to the first one. By the way, for this case, we have this is the pattern, the picture that we are having in this experiment, correct? At the center, we have this very bright spot, represent the center right here, correct? And then we have M equals 1 is when we get the first dark fringe, right? Bright fringe, dark, bright, and so on, right? And the distance from the center to the first one is Y1, from the center to the second one, the second dark fringe is Y2, and so on. Right? That's the idea. Perfect. So let's find this right from the experiment. Now let's use the equation provided right here to find the experimental value. Please show formula in calculations, the data, the values, right? And find the percent error. Part B, now go to M equals 2, correct? The same thing. Find the distance from the center to the second dark fringe. Right, in millimeters. Later you have to convert it to meters. Remember, everything's gonna be in meters. It's easier. Perfect. And then I'll find the experimental value, right? And finally the percent error for part B, right? Let's go to the other case where we have the width, right? The opening equals to 0.008 millimeters. The same thing, right? Let's take the case where M equals 1, right? Find the distance by 1, find the experimental lambda, find the percent, right? The same thing now for part B, go to M equals 2, right? And repeat the procedures. The same thing happens for the last part, right? Repeat the whole thing, correct, as before. So at the end we have 6% errors, right, for this experiment, right? And now let's go to do the measurements. Okay, let's find Y1. Again, we're looking only for Y1, Y2, right, for each case, and then using that data, we calculate lambda experiment. Okay, let's do it. Okay, let's go for case 1, W1. Okay, now case 2, W2. And finally, case 3. Okay, these are all the measurements for this experiment. See you in the next experiment. Bye.